We're going to talk today about availability. So I had some troubles fitting the subtitle in the slide, but what happens when resilience is your primary requirement? So we're going to talk about applications that have to resist outages. So as it was mentioned, so that's me. I get paid by Erlang Solutions to do different things. Most of my time is spent consulting and doing training, which means that I get to talk to a lot of people. That's the primary advantage. So the topic of this talk comes from just looking at what people do in Elixir at different stages and trying to get at least one basic idea that usually takes some time to sink in when you learn the language and when you move on with in your journey to write Elixir applications. You can always reach me at those two coordinates. They're at the end of the presentation as well, so you can always find me there. Now, let's just dive into it. So, who's seen these things before? Now, it's a bit of a trick question because that's the Italian branded version of that object. So that's a pager. In Italy, they were called teledrin. If you remember them, like kudos to you. So, my father is a doctor. He does emergency room and things like that. So when I was a kid and like mobile phones weren't a thing, there were times when he had to be available, and that would be like a 12-hour time period. And what he had to be, essentially, he would need to be in the hospital in less than half an hour if anything happened. So to guarantee that, they would give him one of this, because it's a pager. So it just buzzes, it shows a phone number, and then you just like run to the hospital and then worry about everything else later. But the good thing about it is that it would allow him to spend time home, or like we could go out and do things together, and then if anything comes up, he can always run to work. But he wouldn't need to be confined to just being near the phone. Now, I never heard him saying this, in the sense that, and this is something that as software developers, I think we have a slightly different requirement most of the times. He never said, oh, sorry, I can come to the hospital because the database is down, so sorry, you kind of have to deal with it yourself and then possibly do self-surgery or something like that. So never happened. So the point is, there are things that you do and the things you take for granted in your daily life where availability is the most important concern. But that doesn't seem to be the case in a lot of things we build. And I wish that could change. So backtracking a second for that, things you may have heard as you learn Elixir or Erlang. Like, bear in mind that I will try to mention things like both things at the same time, but realistically, 99% of what we're talking about applies to either language, so it doesn't matter really what you use. It's just principles and some ideas. So, who has heard this? Elixir is fault tolerant. Just like, give me some hands just to, Yes. Okay, multiple sources. I'm definitely sure that talking with people, I said that myself. And then this one, you have to use OTP. Or you need to use OTP, or if you use OTP, it's going to be amazing, like variations of sentences that contain the word OTP. Okay. It recovers to a predictable state. This is like when you got a process, it crashes, it recovers. Like this, we heard these things. So in 2014, or beginning of 2014, when I started learning the language, when I read these things, I was particularly excited about this because it felt like it would solve some of the problems I had with the software I was writing, so I was particularly excited. Except that it didn't, for the first year, a year and a half, I was using some of these tools, but in hindsight, availability wasn't better, not at all. I was just building similar things with different tools, and it wasn't available. And it took me some time to realize, and then I hope that people in the audience just kind of, yeah, that's obvious, that's clearly what it is. But it took me some time to think about it. Is that availability is something you have to design for, because it doesn't just happen, or at least with the tools we use now in Elixir Erlang, you don't necessarily have more availability because you have to design for it. Now, what does that mean? It means that we have a lot of lower level tools that work well together, and we have a lot of good primitives and patterns that we can use. But the biggest problem we need to solve if we really want a good availability is to design a system that makes that a primary concern. And if you don't do that, it's not going to emerge. So there has to be something that you really, in the same way you worry about security or other concerns, it has to be something that you really push forward. So what we're going to do from now and until like pretty much the end of the talk is we're going to work on an example application. And it's going to be like diagrams and color blocks, very little code. This application is called Libra, is because it weighs web pages. So you use it to see how heavy is a web page. It's a web app. And that's just because that's the zodiac sign for a scale. And it's a very short name. So it does the job. So let's look at, like, for example, like a browser version of it. So main interface, you put a URL there, press the button, and what you get is this page where you see, well, if you can, you see that there's a page body sizes, and there's a total size in kilobytes for the page, and there's a list of resources that that page links, each one of them with a weight and a status that represents if the crawler was able to fetch it or not. Now, this page, once you see it, because the inspection can take some time, it updates in real time. So you're going to see the page receiving extra data and then re-render. So the implementation we're gonna talk about is an implementation based on Phoenix. So that's the main underlying framework that we're using. And if we see it, we got like basically 3 separate worlds that we have to get to work with each other. One is the internet on the left, where all the pages we crawl are. This is our, for example, in this specific endpoint where we create a page inspection, it's just a post route that gets invoked when you press the button. And then there's a database. And the database, in our case, is Postgres, but it doesn't really matter. Like it's effectively an external data store. Now, what happens? So the basic implementation that we start from is this one. We fetch the page when we start posting. That's a blocking call. So while the application basically is waiting to respond, and you're waiting and seeing like a beach ball or a spinning wheel, is fetching a page. When it finds it, it saves it to the database. So we go from a page, it parses it, gets out the length of the page, body size, saves it. And then broadcasts, because remember that we have, we are concerned about updating in real time, so we broadcast a page creation. Now, this is not necessarily processed at this point in time, but we do that. And to fetch the assets of that page, we spawn a task, fetch the assets, possibly in parallel, weigh them, and update the page in the database. Okay? Now, let's make it a tiny bit interactive. Is it clear so far? Anyone has any question about this? All good? Okay. Now, this pattern, raise your hand if you've ever spawned a task in a controller. Okay, like not that many people. Okay, this is legit, like you can definitely do it. That's fine, there's nothing wrong with this. So it is a pattern that you can see it used. It does the job. It gives you a bit of extra capacity because you don't have to wait for an expensive operation to finish, and it does whatever it needs to do. Yeah, and at the end you broadcast that, sorry, that you have updated the page. Now, let's go to the other route. You want to see an inspection. Now, each inspection is unique, so you can inspect the same URL twice. You just get back a different UID. So you get a page with that UID, and you read it from the database. It's like boilerplate. Like this could be scaffolded as far as we know. That's extremely straightforward boilerplate control implementation. as the page is real time, there's a channel for it, same routing scheme. You get the page from the database, and then you process any broadcast on that topic that comes in, so that if the page gets updated and the inspection finishes, you can re-render with the extra numbers in the table. Okay. So we're going to use a specific metric to judge this application in terms of availability, which is a telemetry score based on the pager that we saw before. Feel free to use it. As it's trademark, you may need to pay a royalty, but my contacts are at the end of the presentation, so we can sort that out. But in general, the score is not great. Like, it could be better, because effectively we have a very, very, very specific problem, which is this. We have a hard dependency on the database. If at any point the database goes down, we can provide 0% of our service, 0. Because effectively, just to paraphrase like thoughtful Fox Mulder, the truth is out there. So it's not in our app, it's in the database. And in the end, that means that we are confined to whatever availability strategy we have on the database side. Now, our goal is to get this application to work during a database outage. This means completely work, not a subset of the functionality. How can we do that? So we have a master plan for this, in the sense that we're going to see at a high level what's our strategy, and then we're going to look at the implementation for each one of these steps. So if we don't want to depend on the database, we need to keep that data somewhere else. Now, if we use a different database, that pretty much repeats the problem, right? So that's not helping. So the thing we can do is keep page and assets data in memory. In other words, we perform the inspection process and keep the data in memory. The important thing is that we use the same data structures. Now, in the case of using Ecto, for example, and Postgres, you get back effectively structs. So as long as we keep those structs consistent, we may work on a replacement that has the same type signatures, has the same interfaces. And that's important because it makes our life much easier when we do this. So one little thing to keep in mind is that it's important to think about these data structures and try to map them in the same way. The other thing we can do is, as we have each inspection process which is unique and keyed by a UUID, we can have one process per page. Now, the thing to keep in mind is that we can think about this each inspection as a lifecycle process. One thing that sadly I forgot to mention 5 minutes ago is that one requirement that the application has is that these inspections expire after 24 hours. So if you use other services like that, you use them, and then 24 hours later, that data is gone. So in that case, we can design a system where each process manages its own life cycle. Like, each process gets started, does whatever it needs to do to get the data, then basically sets itself an expiry date, like in the future, and then when that happens, it's going to self-destruct. And at that point, writing data to the database becomes something that the process tries to do, but we shift the perspective. Writing that data does not mean working on our primary source of truth. It means having a backup plan when our database goes down. Sorry, when our application node goes down. So the main strategy is that if the database goes down, the data is in memory. If our app goes down, we have a guarantee that we replicate the data to the database up to a reasonable amount, up to a reasonable extent, possibly very, very, very close to the point in time we are. So this process, this worker that inspects pages, we're going to call it the inspector worker, and we're going to build it with a Gen server. So what are the responsibilities of this inspector worker? Well, if we look at time, and that's a 24-hour lifetime for one of these inspections, we know that this process is going to start and is going to terminate. Now, what does it do during the life cycle? So it starts with a URL, and it fetches a page for that URL. Once you have that and you know where assets are, you fetch the assets. And then you save that to the database. And the important thing is that throughout this process, let's make it less confusing. Throughout this flow, the process can respond to questions. So if you just fetch the page and you ask the process, okay, give me the page, what's the state? It's going to give you a page without assets. If you fetch the assets, it's going to give you that page with assets. So it gives you that from its own state, from its own memory, so it never goes anywhere else to find it. And then once it's done its fetch operations, it can save it to the database. Then after a bit, after 24 hours, it will terminate. When it terminates, it deletes the data from the database. So we have a clean life cycle that gets the data where it needs to be and removes it where it doesn't need to be there anymore. Now, let's implement that with GenServer 2. So again, same time. So we start with an init where we receive a URL. Now, we can choose to fetch at this point, which is a bit expensive, and it's a blocking operation, or we can do it asynchronously. The thing that we need to decide for this is if we care about the existence of that URL as a result of our inspection. For example, if we want to say, hey, you try to inspect this URL, and it's a 404, then we can do this asynchronously, because the inspection is still valid even if you pass a URL that doesn't exist. However, if you pass a URL that is badly formatted, then the process cannot do anything, and it could just like self-terminate at that point. So in the init, assuming that we care about 404s, the process casts to itself. So fetch the page, then it does that. Then after that, it casts a fetch assets, and it does that. And after that, it casts a save, so it does that. So we do that in chunks. You can try to compress some of these steps together. That becomes like mostly a choice. But effectively, we are just trying to make this like, we just do like small atomic operations to keep the process as unblocked as possible. You can even make it more complicated than this, but let's just stop at separate callbacks. And after that, we set up a message, like a send after message that will expire the process. Now, expiring means we handle an expire message, and then we stop at that point. And when that happens, we delete. So this way, we make sure that any situation where there's an abnormal termination, the data in the database would be deleted. Now, it doesn't happen very often because of the life cycle, but it gives us a sort of like a safety net to make sure that the data remains as consistent as possible. Now, what are the benefits? Each step is a callback definition, which means that it's a public function, which means that you can test it independently. And each step schedules the next one. So if you squint a bit, this is like a state machine in disguise that goes only in one direction and doesn't fork. So it's a very simple state machine. But it does mean that you always know what's going to happen next in the process lifecycle. And the other thing is that self-destruction doesn't depend on an external scheduler or polling mechanism. You don't have to have a process that, or something that every 5 minutes says, okay, where do I have to delete now? Which process do I have to kill? Each process manages itself independently. And finally, persistent is an implementation detail because it is in one function, it is in a callback, and then so far, because of the nature of the feature, we are basically using Postgres as a key value store. So you could potentially swap this for something else that has different properties in case you have other concerns. For example, around a data store that is maybe more available or something that gives you different properties in terms of speed of query and things like that, whatever is your concern. But it means that your primary interface is not going to be the database anymore to get this data. Now, we looked at a process in isolation, like I have a URL, I want to start inspecting this URL, I'm going to spawn a process. And that could be like a floating process in your system, completely like without any connection, any link, no monitoring. in your system, in your application. That's not ideal because what if that process gets into a weird state where the network becomes unreliable and suddenly you have zombies everywhere? And apparently that's a bad thing. So we need a supervisor. And in this case, we can start with a simple one-for-one. A simple one-for-one supervisor is a supervisor that is there are different types of supervisors in OTP. This one particularly takes a boilerplate definition, so it knows how to spawn one specific type of worker and just that one, but it can have as many of them as it needs. So it can spawn 1, 2, or 3, and it keeps tabs on them. It knows which ones are alive and which ones are not. So what we can do is we can have an inspector supervisor that each time we want to inspect the URL, we ask the supervisor, hey, give me a new worker that does this. And by doing this, we have a few important properties at this point. Then we have an API to spawn workers, and an API is that starts hiding a bit of the implementation detail. We know that we're spawning a worker because we know that we're interacting with the supervisor, but we can hide some of the details for this. The workers are monitored and restarted in case of abnormal termination. So, for example, a 404 is an acceptable error that shouldn't cause our worker to go down because it's an acceptable result of an inspection process. However, if you have, for example, an internal network error because the machine that is doing the inspection ends up dropping off the network, and you get, for example, like an NX domain, I don't know how to go to the network error, you may want to let that just bubble up as a critical error and just let the process crash, because that way the supervisor will restart with the same URL. And that happens up to a certain number of attempts. So you know that this way you can distinguish and you can start to discriminate between acceptable failures that are semantic, that have to do with your domain, and failures that are absolutely exceptional events that you just don't want to deal with in an explicit way. And the supervisors always know which children are alive. So you avoid the problem of the zombie process. Now, next problem. Are we good? Is everyone okay? Okay. So, routing to a worker. Now, the problem is this one. I wish I should have used this as a screenshot that one of the other talks from yesterday about visualization, but too late. Once we have to fetch a page, in our new version of the system, what we need to do is basically we have to go from an ID, from a UUID to a process. So we have to resolve that in some sort of ways. So the problem we had before was get the page from the database. Now we have a problem of finding a worker for this. Now, that means that each worker needs to have a UUID. So before, when we were writing to the database, we were relying on Postgres to generate the UUID, send it back to us. Now we need to handle that ourselves. So we start an inspection, we assign a UUID to that process, and that process registers itself with that UUID as a name. To do this, we need to use a process registry, because by default, process names are atoms, and you don't want to cast a UUID string to an atom and use that as a name, because that introduces a memory leak that cannot be resolved without rebooting the node. So it's important to keep in mind that when you have to map types that are not atoms to processes, a registry is always your best bet. So what are we going to do about this? We get pages, we have to find a worker. We wrap a call to the registry that we have in our application, so we can use this registry, wrap it, resolve to a worker, and use that to get the data we need. So at this point, the benefits are that each worker manages its own name. In other words, it's a responsibility of the worker to register itself with the name. We don't have to do that from the outside world, which means that we don't have to manage that synchronization. Each worker starts, declares its own name, registers itself, and the registry will get updated automatically, because it's monitoring these processes when the workers die. So we are a very good situation where our registry knows exactly which processes are alive, in the same way the supervisor does. That just happens automatically, so we don't have to do that ourselves. So once we declare this flow, then it will work. And because we're working on a single node, Elixir 1.4 ships a built-in local registry that does exactly this. That is by far my favorite feature of that release, together with enforcing parentheses for function without arguments. That really does the job. So what we've seen so far, if you exclude the fact that we're using Phoenix, we are only leveraging standard library. So we're not pulling in any dependencies. So all of this is possible just by using tools that the language provides by default. Now, it is quite a bit of machinery, though, that we put in place. Like, we got workers, we got a supervisor, we got a registry in place. No one else needs to know about this from the outside world. So what we need a public API. And the public API purpose is, let's make sure that all of these implementation details do not leak to the callers and the consumers of this API. So exactly because of that, in this slide, which is like, that's just a bit of code about how this public API could look. On purpose, there's no implementation, in the sense that the perspective we have from the point of view of this model is that we care about providing a consistent interface. Our web layer will consume only this file, will consume only this API, and we give really strong guarantees about the types that we return, in the sense that when we process URL, we get back OK, and the UUID for that inspection. We don't know that there's a process behind it. We don't care. At this stage, it just doesn't matter. In the same way, once we have a UUID and we ask to get the data about that page, we get just the page data. We don't know that that comes from the process. We just know that you got a page that may have some data in it, or that it's incomplete or complete. We just don't know. But we don't really care. At the same time, we return errors that make sense. So get page, if you look at it, it is a notation and a specification that it could be something that comes from a database, right? You just OK and the type, or error not found and not nil, because personally I prefer explicit errors instead of nils. But in general, we just keep a predictable API that hides the implementation detail. So the consumer of the API is unaware of this implementation detail. We can refactor the entire thing without affecting anywhere else in our application. Now, this particular property is also one of the things that I think it's important to think about, especially with the next releases of Phoenix, but in general in Elixir and Erlang, is that having a public API with a very focused API usually means that you can easily work on the internals without affecting the other parts of the system. So it's important to just like make a bit of extra effort to do that. Now, we started with one specific requirement, though, which was surviving the DB outages. And I would appreciate if anyone laughed to the pun at the bottom, just because I think it's pretty good. Try to the rescue. Even out of pity. Yeah? Come on. No, we want to survive DB outages. Different strategies for this. When you deal with resources that can fail, there are certainly different patterns you can use. And like some people introduce circuit breakers and other like patterns to survive outages. In our case, because we have a very focused usage, and we basically know what we want to protect against, we can use a very focused try rescue, in the sense that we try to save to the database, we rescue a specific exception, and not all of them, just one, and possibly retry, same as when we try to delete the page from the database. Now, try rescue should be used sparingly, in the sense that it may hide errors that would just be better. You would just be better off letting the process that caused that function crash. So you may end up rescuing, if you're not very specific, things that you would want to bubble up because you would want the process to restart to a predictable state. See, I mentioned one of the sentences that everyone says. And you want to rescue relevant errors. In our case, if we care about being able to connect to the database and having that database online, that's the error we want to rescue, because that represents the inability of our system, of Ecto in this case, to open a connection through DB connection with the database. We also have the opportunity, because we have two specific points in our code that talk to the database and they encode the possibility of a failure, to think about what we want to do when the failure happens. We can retry, so we can schedule the process to retry, and we can do that with a backoff. So maybe if the database is down, chances are that it may be down for another few seconds, so why don't we wait 5 seconds to try to save again and retry. So all in all, there are different things you can do even to improve on that, but the point is that you have like a specific point, and only one in your code base, where that concern can be expressed and you can work on the code for that. So what's the road from here? So the road from here is that we haven't touched on two specific topics. First one is restoring state. So the node goes down, Postgres is alive and well, we bring the node back up. How do we restore the processes that are supposed to take care of the inspections? Option one, we read or we stream the relevant entries from the database, meaning pages that are not supposed to be expired, and we spawn a process for each one at the right stage. So if the inspection was over, so the inspection, because the page was saved in the database, it was over, so we use that page record from the database as a state, and then we calculate how much time we have left for the expiry. That's option one. One thing to keep in mind is that, first of all, better to do this in batches. And the second thing is, when you do, this is in general, when you do like long-running operations that have to deal with the database, sometimes if you just write that code without like a little bit of extra care, you may end up hogging your main repo because you keep checking out connections, for example. Like that's not necessarily what we're doing here, but it happens. So in this case, maybe a separate repo and a separate pool of connections could be good, because that way you can guarantee that the other repo that in the meantime can be used to serve requests is available. The option two is lazily spawn workers. In other words, we start, let's say that I want to show ID 1 to 3. I look for a process with that UUID. If it doesn't exist, I check in the database if that UUID exists. And if that page is supposed to be alive, if it shouldn't be deleted, then I spawn a worker for that. Now, that is a lazy. That could work better in case you have like a huge amount of data. However, it really limits availability because you're doing a query to the database at that point. So you may have, if you're not available at that point, then you're still back to square one. The other elephant in the room is the going to single node to multi-node, because we built a stateful service right now. And that means that the memory of that service becomes a formal state that, in the case of a multi-node setup, we have to manage. Now, that means, how do we do with that? There are so many ways you could approach this. You could, for example, replicate that state on each other node that you have. And because we are working with something that only moves forward and has very little conflict possibility, then this could be something that you handle with a pub subsystem, for example, and something that could just give you the ability to replicate each inspection on every other node. Now, the problem with that becomes memory effectively, because even if you have 5 nodes, effectively you have the same amount of memory no matter how many nodes you have. The other option is to shard this, but then you have to think about what happens if one node, specifically node, goes down and you need to rebalance, and maybe that data goes lost. So certainly increasing or moving towards like a strategy that wants to increase availability comes with other challenges that you have to think about. The single node registry should become a distributed registry. There are different options for this, nothing built in Elixir, but you have to think about that as well. And finally, this is something that is a side effect of thinking about a multi-node architecture, is that you can deploy, think about these components as deployed independently. The likelihood in this application is that you may gonna have more work in inspections compared to the work that the web stack needs to do, because the web stack is very minimal. So if you find yourself that you need a couple of web nodes and 5 inspector nodes, you may need to think about how to split that code so that you can pack a node that is just a web node and a node that is just an inspector. An umbrella could help you with this. Small aside, the ability to build nodes independently and pack your applications together, that is by far the biggest advantage of using the umbrella. Like segregation in terms of code organization, you can do that in the lib folder. You don't need an umbrella for that. The umbrella applications really shine when you can pack independent applications together in different node layouts without having to restructure your entire application every time. So in general, designing for availability requires thinking. It is worth the effort because you can be available. And that's important. Maybe you have a service that maybe it's mission critical, maybe not, but in reality, because outages happens always when you don't want them to happen, if there's any time you want them to happen. But in general, if you have like a spike in traffic for a particular promotion, that you want it to be available. So, any questions? I'm definitely willing to answer, like compared to, this is just to give you expectation that I can do a better job than that. No.
Should I be bracing myself here, or?
Eh?
I said, should I be bracing myself here?
Yeah, no, it's fine. Well, thank you. This is my in case you need to reach to me. Again, these are my coordinates. Feel free to ask questions and anything like that. If we have time, I can take questions now. Otherwise,
yeah, I think we have a bit of time. Does anyone have a question, or? I'll pop back there in a moment as well.
So thank you, very interesting speech. So you say only rescue well-defined errors, and you're not the first to say that, but how would you actually do that? Because we're talking about what you want to secure ourselves against is the database going down.
yeah.
It's like, well, all the database being unavailable, and it can be that in so many ways. Like all of a sudden, your machine says, I have no free port to talk to that machine, or I've dropped off the internet, or I have a power glitch, or whatever. There's so many. How do you enumerate all of those?
That really is dependent on the library that manages that connection part. Like in this case, like that DB connection library, which if you have questions about, the author is in. I don't know if he's in the audience, but I don't see him. I don't see him in the audience, but. He has, no, seriously speaking, it's just that specific library, there may be other exceptions that you want to rescue, but it's a matter of seeing how that library is constructed, and if it does that, if it throws exception or raises exception for those particular events. A different database may behave differently, may even just like not even throwing exceptions. You may even just get, like for example, I'm working with CouchDB, and CouchDB has an HTTP interface, so I may get a 500, or I may get a 404, or a 400, it depends. So it really depends on that specific driver. In this specific example, it was Ecto and Postgres, so that would be the thing you match for, although there may be other instances. I normally just worry about that because that's the most frequent one that I see.
There's another question over here.
Hi, thanks for the talk. Could you elaborate on the last part where you talk about how you would deploy different kind of nodes to handle the memory issue? Because I'm not sure I got it.
Okay, you mean like capacity issue?
Sorry,
like just being able to serve more inspections, or are you talking about the data?
Well, the data part, the fact that if you unload everything in memory, it's become complicated.
So the simplest way to tackle that problem is to switch to a high available data store and pretty much discard whatever we talked about for the last 45 minutes. There's a simplest option that requires less work on your end. What you basically need at that point is assume that you have 10 inspections in node A. Now, if you can afford to lose that data when the node goes down, lose it completely, and another node comes back up, and you're able to define how that node needs to restore. So for example, that node knows how to grab only the subset of the data in Postgres that pertains to its own state. For example, you could use like consistent hashing on the URL so that you partition the data in a predictable way. At that point, you somewhat replicate the pattern of restoring the data on a subset of the data for the node that's coming back up. That's one possible way. But that gives you a window of unavailability because you're doing that job. The other option would be to have nodes that the data is replicated on, for example, over 5, 7 nodes on 2 other nodes. And then once a node goes down, the other one takes over. Now, none of these things are just come out of the box. You can look in the libraries for them. But in some ways, that's the principle behind like this. The React as a database kind of works in a lot of scenarios like this. So you can, but the basic point is that it's not super straightforward, and there are definitely different trade-offs that depend on how much data you have, what kind of load you have, and what kind of consistency requirements you have, in the sense that it may be acceptable to have like 10 seconds of unavailability for that specific page, and that's a trade-off that you're willing to make over total unavailability in case of an outage. Does that answer your question? Okay, thank you.
Does anyone else have another question? Super. Can I just squeeze by?
Thank you for the great talk. I'm interested in this as well. It seems like you're interested in having stateful gen servers, right? That seems to be kind of what you have created. Is there any other research that Erlang has done? Erlang's been around a long time. This can't be the first time that someone has tried to make a stateful gen server. That like if it crashes, right, it comes back with the state it had. Do you know of any other research? Because I'm looking for something like this too.
The simplest thing you can do is just move the state out. So one thing that is possible to do is you use the gen server just for the life cycle, but even in terms of keeping the data in memory, you move that data in another process that owns that memory, so that when the gen server goes down, you don't lose that data. You could use like an ETS table that has that is like fairly protected. Mainly, it's owned by your main application process, or it's got like a good strategy for recovery, and then you move that data into the table. And at that point, you could also read from the table directly. You're not tied to that. But at that, it makes it that the gen server worker doesn't die. So it doesn't affect the existence of the data. That doesn't protect you from the node itself going down. And also the other thing is that then you have to worry about synchronization, because, and in terms of like, so basically you have to do the same work twice, delete from the table and delete from Postgres when it's time to expiry. So that's the other thing.
Does anyone else have another question?
All right, cool, thank you.
Okay, cool. Thanks very much, Claudio.